For over a century, the scientific consensus on the destruction of Pompeii has relied on a two-part model. Structures failed because of the accumulating weight of falling pumice and the lateral force of pyroclastic currents. While we have extensive records of earthquakes striking the city in the years before 79 CE, this standard model overlooks a simultaneous hazard acting on the buildings, earthquakes occurring during the eruption itself. The evidence for this overlooked force was recently uncovered during modern excavations at a site in the center of the city, the Insula dei Casti Amanti. Early excavations at Pompeii often lacked the precision to capture microstratigraphic details. They cleared away the physical evidence needed to separate overlapping destruction events. This stratigraphic column shows the sequence of the 79 CE eruption. At the bottom are EU2F and EU3F, thick layers of Plinian pumice lapilli. On top of that is EU4PF, a layer of gray ash deposited by a pyroclastic current. These deposits map to a timeline. The pumice fallout lasted for about 18 hours through day 1 of the eruption. The EU4PF ash layer marks the dawn of day 2, when the eruption shifted into its caldera-forming phase and unleashed pyroclastic currents. When buildings are buried by volcanic material while simultaneously shaking from earthquakes, differentiating the cause of a wall collapse becomes an intense forensic challenge. To accurately model the mechanics of this catastrophe, we must conduct a rigorous comparative analysis to separate seismic damage from volcanic impact. This 3D structural map shows two adjacent spaces in the house of the painters at work, Room A on the left and Room 22 on the right. During the 18-hour Plinian phase, white and gray pumice lapilli poured through doors and windows, accumulating in deep, sloping mounds. Because of the sloping roofs, most of the pumice was directed into the outside alleyways. Without that vertical load, the masonry walls remained intact. Room 22 establishes a clear baseline for volcanic destruction. As day 2 began, the EU4PF parental pyroclastic current arrived, moving in from the northwest. This current hit the northwest wall of room 22 at a perpendicular angle, exerting an estimated dynamic pressure of 3 to 4 kilopascals. Under that lateral pressure, the masonry fractured. The wall's upper section toppled southeastward. As it fell, the current deposited a thin gray ash layer onto the floor just before the blocks crashed down. Once on the ground, those fallen blocks were completely entombed by the rest of the ash settling out of the current. Room 22 provides a volcanic signature: perpendicular impact, downcurrent toppling, and simultaneous ash deposition trapped beneath the debris. Returning to our 3D model, the structural damage in Room A directly contradicts that volcanic baseline. We can see this clearly by isolating Partition Wall 1. Partition Wall 1 is oriented northwest to southeast. Because it sits perfectly parallel to the direction of the pyroclastic flow, it was not exposed to that dynamic pressure. The wall was also physically shielded. Seen here with ancient amphorae, the room's western sector was filled with deep pumice, creating a dense granular buffer. Instead of toppling, Partition Wall 1 experienced a different type of failure.
A horizontal shear plane fractured directly through the masonry, 60 to 70 centimeters above the floor. A massive block of the wall, measuring 200 by 140 centimeters, sheared horizontally to the northeast. It moved as a solid block and dropped vertically to the ground without tipping. This horizontal shear and drop motion requires immense lateral ground acceleration. A fluid density current cannot produce this specific mechanical failure. The stratigraphy locks in the timeline. The sheared masonry block rests flush on top of the EU3F pumice layer and is entirely draped by the EU4PF ash. This places the collapse in a highly specific window, after the pumice stopped accumulating, but before the pyroclastic current swept into the room. Chronologically, based on the stratigraphy, Room A was destroyed by a severe seismic event occurring precisely between eruptive phases. The structural timeline is independently corroborated by the human remains permanently locked inside Room A. Here we see the remains of individual 2. He was discovered with his lower limbs pinned directly beneath the heavy, fallen masonry block. Analysis of the bones reveals a specific trauma pattern. Both victims suffered severe serial rib fractures, known as flail chest, alongside comminuted pelvic fractures. These extreme compression injuries match the trauma profiles documented in modern earthquake victims caught inside structural collapses.
This directly contrasts with standard casualties in the area. There are no markers of thermal shock or asphyxiation prior to the impact. Furthermore, the internal skeletal volume was filled with loose wall debris rather than fine ash. They were buried instantly by failing masonry, not enveloped by a pyroclastic cloud. Individual 2 was found in a huddled, defensive posture. He was conscious of the violent shaking and attempted to take cover before the wall failed. The forensic anthropological data fully verifies the structural engineering. These individuals were killed by an earthquake. Zooming out from this single insula allows us to reevaluate the broader timeline of destruction across the entire city. This timeline shows the moment the magma chamber's roof fractured, the caldera collapsed, triggering a massive seismic swarm exactly between the pumice fallout and pyroclastic currents. This spike generated ground accelerations capable of shearing unreinforced masonry across the urban grid. This forces us to challenge the assumption that all the victims found indoors within the pumice layer died purely because their roofs collapsed under the dead weight of the rock. It is highly probable that many roofs capable of withstanding the weight of the pumice were actually compromised and brought down by these intense tremors. This seismic swarm is likely what finally drove the remaining populations out of their shelters, pushing them outdoors exactly in time to be caught by the incoming pyroclastic currents.
We can no longer analyze destruction layers by treating geological hazards as isolated events. Accurately reconstructing ancient catastrophes requires treating volcanic and seismic processes as tightly coupled forces. By integrating structural mechanics with microstratigraphy and anthropology, we can pinpoint